StructLayout. Let's find out. First of all, I'd like to thank Landsweeper for letting me borrow their studio. It's pretty cool. Second of all, this is definitely a more niche topic, but I guess learning about how memory works in .NET never hurt. So right here I have this class. This is a struct. It has a short value which has 2 bytes, an int which is 4 bytes, and then just 1 byte at the very end. And then we have this struct layout right here. So what this does is the following. When your system needs to create a new instance of the struct, it needs to allocate some memory, and with struct layout we can decide which of these bytes goes where. Now, first of all, why do we even care about that? Well, the first thing you're probably going to run into is interoperability with some other language like C, C++, or Rust. For example, if you want to create a new file on Windows, you have to call this function. Now, normally you don't have to call this yourself, you would use system.io. There are many functions in Win32. So if you're unlucky, you might have to call this manually using pinvoke. And then you'll see that, well, I have the definition of the function right here, and I have to pass along all sorts of stuff. For example, this security attributes. Now you can see that this is a struct defined in C++. So when we call it, we have to match it exactly in C#. Another example could be high performance code. You can really optimize for either read speed or memory optimization. Be a little bit careful here because performance tuning can go both ways. A third example would be memory mapped files. Imagine that you want to create your own SQLite. Yeah? You want to know exactly which byte goes where. And finally, another example would be protocols. If you're passing a protocol, you have a bunch of byte arrays and you want to extract some information, you could try to match that. However, little caveat here, you probably want to take endianness into account as well, which we'll talk about in another video. Alright, so back to this example. So whenever you specify struct layout, you have to specify this layout kind as well. And let's start with this one, with sequential. What does that mean? Well, it means that the order in which we specify our fields is the same order in which we store our bytes in memory. So how many bytes in total do you need to store this struct? Well, if you're a reasonable person, you probably think 7, and that would be incorrect. It's actually 12 bytes. But why? Well, this is where alignment and padding comes in. Let's take a closer look. So you might think the memory storage looks a little bit like this, but in fact, it looks like this. So there is some padding in between the short and the integer, and there's also some padding at the end. Now, at first glance, it may not be completely apparent why this is the case, but if we reorganize our image here, then this is a lot more clear. Now we can see that each value is nicely aligned on this 4-byte boundary. You see, when your system fetches information from your memory, it doesn't do it 1 byte at a time. It usually fetches information per 32 or 64 bits. In other words, 4 to 8 bytes. So if your data is misaligned, like so, well, you're going to need 2 operations to read this full integer. So here is what a collection looks like without any padding. And this is the same collection but with padding. So yes, you are using more memory, but the access to the individual values will be much faster. Generally speaking, alignment helps for performance, cache efficiency, and your sleep at night when you've used that int where that should have been a short. Okay, so how do I actually know that this is the case? Well, you can measure it. So I have an operator for that. It's called sizeOf, but unfortunately sizeOf is something that you can only use within unsafe blocks. So the alternative would be marshal.sizeOf, which basically does the same, except this one is set at compile time, while this one needs to be figured out at runtime. So if you are in an unsafe area, you would prefer that one, but you don't have to specifically create an unsafe area just for measuring the size. Okay, so let's see, and indeed our structure is exactly 12 bytes as we predicted. Right, what about the alignment? Do we know where the padding goes? Well, yes. You can do that with the following. You have this marshal.offsetOff. So we can check like, hey, I've got this short value, this int value, this byte value. Where is it compared to the beginning of my struct? So if you run that, we should see that indeed I have the short value at the beginning, then 4 bytes later I have my integer, and then 8 bytes later I have my byte value. So nicely aligned to that 4 byte boundary. Let's try something. Let's go here and let's move this byte value up a bit. Now take another guess at how large this is going to be. So let me just run the code immediately, and we'll see that in this case it is 8 bytes. We knocked off 4 bytes, and you can see that I have the short value, we have then the byte value, and then we have the int value. So it actually looks like this. So that's pretty cool. By reorganizing your fields, you can use less memory while still being as performant as before. Pretty nice. Now, if this kind of optimization is all you're looking for, well, look no further than not sequential, but auto. Auto will automatically find the best configuration for your struct. This is primarily useful if the struct stays within the realm of your application. However, most of the time, your struct will need to follow well-defined recipes. So you probably want to use something like sequential or maybe explicit. We'll get to that one. Okay, so let me just put the byte at the end again. So we should have our 12 bytes again. And let's replace this int value with a long value. Now that should increase the value with 4 more bytes, right? Well, let's see, and no, we now have 24 bytes, so it actually doubled in size. And you can see why that happened. Yes, my short is still at 0, but the long value is no longer at 4 bytes, it's at 8 bytes. And the last byte is actually starting at byte number 16. So it actually looks a little bit like this. We no longer have the 4 byte alignment, we now have 8 bytes. Why is this the case? Well, because the long is longer. You see, every type in .NET has certain align requirements. An integer needs to start at a 4 byte boundary, but a long needs to start at an 8 byte boundary. So that's why it cannot start here and has to move here. And it determines the boundaries for my entire struct. So hence the alignment size is now 8 bytes, resulting in 8 bytes for the short, 8 bytes for the long, and 8 bytes for the final byte. If you want to specifically control this alignment, there is this property that you can use. It's called pack. Now pack can have values 1, 2, 4, 8, 16, 32, and so on. So if you set the pack value to 1, we will have no padding at all. So we should get 2 plus 4 plus 1 byte. And indeed, we have those 7 bytes and they are aligned exactly as expected. So that's what it looks like. If I set pack to 2, I will need 8 bytes in total, which is 1 byte of padding at the end. And if I set pack to 4, well, we're back where we started. We get our 12 bytes and that padding again. I think you get the picture. Now, there are some exotic cases, like if you set pack to 8, you might think it looks like this. But in fact, it looks like that. So alignment is actually quite complicated and it's best to double check. I'm not going to bother you with the details of this little example right here. You can make it as an exercise. Now, there's one more property I like to discuss. So if we go back here, I can specify this size property. Now, with size, you set the total size of the struct, but of course this cannot be smaller than whatever the pack and alignment dictates. So if I set this to 4, my size will have to be at least 12. But I can set it to larger values. I can set it to 16 or 32 or whatever. And if I run this, you will see 32 bytes. The alignment is as expected. There are just a whole bunch of bytes at the end. So this is primarily useful if you want to reserve some bytes for later use and you don't want to change the size anymore, or you just want to ignore a whole bunch of bytes that you're not interested in. Another trick that you can use is using this fixed byte array. It needs to be fixed because you're in a struct. It cannot be variable, it needs to be exactly this length. You can also use that if you want to fiddle around with padding yourself. A nice little use case of this is, well, a MAC address of a device is exactly 6 bytes in length. So you can easily capture it like this. Okay, so if the alignment rules that we talked about so far don't make any sense, don't worry, you can still use this. So this is by using a layout kind explicit. So what does it do? Well, it allows us to specify the field offset exactly. We are in full control of where these values go. This is the easiest way of matching those types in C and C++. So in this particular case, we might be optimizing for memory usage. However, generally speaking, alignment is more important. Now, there are a couple of very interesting things that you can do with this explicit layout. For example, let's take a look at this. So right here, I've got this struct, and it holds this unsigned integer. This is 4 bytes, but this total struct is only 4 bytes in total. If we take a look at the other ones, we just have 4 individual bytes here, and they have field offsets of 0, 1, 2, and 3. So that means that these 4 bytes and these overlap. And this is actually a nice trick to reference the individual bytes of my unsigned integer here. Okay, let's play around with this. So I'm going to create a new instance of this, and I'm going to set the first byte to 1. So let's see which value is produced. And I get an integer value of 1. Okay, cool. Let's try it with the second one, b1, set that one to 1. And now you can see that my integer value is 256. So it appears that b0 is the least significant byte, then b1, b2, and b3 is the most significant byte right here, which is also an indication that I'm running on a little endian system. Once again, separate video about that. Okay, so here's another interesting thing that you can do. With flags, you can actually control individual bits. And I'm going to need that in the following piece, because I got this thing, it's from a protocol where the first byte actually has a bunch of flags, and then it is immediately followed by 3 bytes, which is a 24-bit number. Now in .NET we don't have something like a 24-bit number, so I'll have to apply some trickery to be able to get and set that. So if I take a look here, you can see that yes, indeed my flags are positioned at the very beginning, and then I have this unsigned integer which is also at the very beginning, but of course I don't want to mess around with that first byte here. So that's why I added this property. Once again, I'll leave this part as an exercise. Try to figure it out. So let's mess around with this a little bit. So I'm making a new instance right here. I set the value and I'm going to enable the B flag. And then I'm just going to print every one of those individually, A, B, C, D. Then the hidden value behind the scene, and then the actual value right here. So this will probably be a lot larger number than this, since we'll have a 1 in there as well. Okay, so let's see, and indeed, B is true, the value has been set correctly, and this one as well. So here's another trick that you can do with this. As you can see, I've got 4 bytes coming from somewhere, my network for example, and then I can use this Marshall pointer to structure, which basically means, hey, take these bytes and dump them in the memory of this structure right here. I don't have to do any additional conversions, it just straight away puts it in there, which is a very efficient way of then reading these individual values. So I set the flags here, so I should have 3 of the 4 flags enabled, and then I put this byte here, which should be the least significant byte, so my value should be set to 1. Let's see. And indeed, 3 flags that are true and a value of 1. Big caveat here, do watch out for endianness. This assumes that the order of your bytes of your system is the same as wherever this came from. Separate video. Okay, so let's wrap up this video. There is one property that we haven't discussed yet, which is this one, char set. I'll probably make a video about marshalling soon, and then we'll talk about stuff like this. Alright, so that concludes the video. I hope you learned something. Absolutely. Thanks, Edwin.